Penn State's Supr 2G is a bench-scale continuous flow hydrolyser system developed to pre-treat lignocellulosic biomass for energy production. It is housed on the main University Park campus, where it is used for academic research. It is also available to the public. A team of engineers from Geosyn Fuels recently arrived to spend several weeks turning pallets of bagasse into gallons of slurry.
This is Mark Sines, gentlemen. Hey Mark, pleasure. Mark's the director of our shared fermentation facility, and he'll be your host while you're here working. Great.
The computerized system controls will allow them to test a variety of residence time, temperature, and pressure conditions. After some experimenting with the moisture level and particle size of the feedstock, things are rolling along, and Sean takes a few minutes to describe the process for the folks back at the home office.
All the controls are on the touch screen here. Couple major screens, this one here. This is where we actually set all of the conditions throughout the run. So we've got the feed hopper, percent speed, screw feeder, percent speed, and reactor speed. That's the three major screws that we have throughout the system. We also measure torque throughout the system to see whether we're overloading our screws, particularly on the screw feeder is where that's critical. And then we can also input our set point for pressure. Right now we're slowly ramping up, so our current pressure is 5 psi and our set point is 15. So the PID controller in there will slowly ramp up the temperature as we go based on the error there.
That's what that is?
This is a steam control valve, yes. So as you can tell, to try to achieve that pressure, it's opening about 30%. So it will, because of the controller, it will vary in steam flow depending upon what the desired pressure is versus the actual.
The last thing that you control on here are the discharge valves, and we'll talk a little bit more about that later. But you cycle the discharge valves individually on time to pressurize up the system and then depressure to blow the solids out. The system, as I said, consists of 3 major screws. The first screw is the feed hopper. That's this one here. You add the biomass that you're working with into the feed hopper, and it comes down to a screw that feeds it towards the front end of the machine. It eventually drops through this connection here down into our plug screw feeder. So when you're running steady state, you should see a consistent flow of feed there, which then gets compressed down into a plug that can maintain the pressure as it continuously feeds into the main reactor screw itself. It gets progressively tighter and tighter flights as you go across the screw, so it squeezes the material and gets it more and more pressurized, more and more compact. And any excess water that cannot maintain within the solids then gets squeezed out of these holes here. Gets squeezed out and drips down. For our purposes, we have to keep track of that so that we know how much chemicals stay in the material. The noise there was the feed pump on the boiler. So it's got to push against 250 psi of steam in order to supply water, fresh water to the boiler. So as you start consuming steam, it's going to draw off that steam and it has to replenish the water over time. So that kicks on periodically, maybe a couple times an hour just to replenish our steam supply. One of the problems that we've been having running this machine with our particular feedstock has been flowability of the feed itself. We've got a lot of larger particulates, and we've been having it get bridged, particularly right in this general area. Here's the feed hopper screw comes through here, and then it drops down to go down to the plug screw feeder down here. So one modification that Mark pioneered was this adapter up here. We actually have a viewport on the top here that we shine light down so that we can see whether the light is continuous or not.
I'm on hopper control to make sure we don't get bridging and a loss of feed into the plug screw itself.
As we showed you before, the plug screw feeder, the outlet of the plug screw feeder are these interchangeable nozzles. And each of them have a specific inside diameter. Those are characterized and known. Each material you've got to work with the inlet nozzles, and there's about 6 or 7 of these. So until you find the right nozzle to give you a good enough plug to maintain your pressure. So here's the main reactor body itself. The plug screw feeder feeds on this end, and you've got the drive that turns a internal screw in there. We set the speed of that screw in order to slowly move the material throughout the chamber here. You got a horizontal reactor chamber up until this point, where the screw ends and it drops down our drop leg here, and then the differential pressure as it opens to atmosphere here will allow the pressure to equalize and flush all the solids into our chamber right here. Once it then closes and is at pressure, this one will open up and allow the pressure to equilibrate with atmospheric going to our blow tank to flush all those solids back out. And that's just a continuous process to keep those solids moving and out, and to try and control your residence time. The majority of your residence time is up in here. Residence times can vary from about 1 minute, minute and a half, down to as long as potentially 20 or 30 minutes as you ratchet that screw speed down. The steam is actually injected. There's 3 different places that you can inject it. We're currently injecting right here, directly above where the biomass is being fed into the machine. You can have a couple different reaction ports. We believe that maybe that it was actually designed so that you could potentially inject acid or something like that into here rather than having to feed it with the feed itself, but that would require additional pumps and everything, and the unit at the moment is not capable of doing that. You see these 2 tubes. One of them is coming from the port that I showed you earlier. That's in case there's a reversal, which if the plug loses its integrity and pressure backs up, it'll direct the majority of the steam up and out here safely outside the building. This other tube here is pulling the flash steam. Every so often you hear that puff. That's coming from our flash tank. Each valve cycle, you're injecting it into that tank at a tangent to the wall. So it causes all the solids and liquids to separate to the outside, all the vapor and gas to go to the inside, and then the gas goes up and out. All the solids and liquids should travel down and be collected into a bucket. Right here is our steam flow meter. It actively measures the amount of steam that we have being supplied to the instrument itself. That doesn't respond back to the PLC, but you can actively watch it to see roughly the amount of steam that you're consuming throughout the process. We've got a manual pressure gauge back here, so you can verify what the pressure is within the reactor. We've also got a temperature probe here that measures the temperature within the reactor, and then another automatic pressure gauge right here. This is what responds back to the PLC to report the pressure, and then controls the pressure based on the valve itself, as Mark showed you earlier. The solids themselves come and are collected in a bucket down here.
The buckets of slurry containing the solid and liquid fraction are refrigerated on site before shipping. An oven, desiccator, and scales are on hand to collect moisture level data, and an industrial grinder is available to resize the biomass. The Supr 2G continuous flow hydrolyzer. Come see it for yourself.